Hi, welcome back to my channel. My name is Gina. In the last video, we talked about the determinant function. If you haven't watched the video, I'll put the link up there. In this video, we are going to continue to talk about the determinant. We are going to talk about the effect of the elementary row operations on determinants. Remember, we have three types of elementary row operations. We can either interchange two rows, so we interchange ith row with jth row. The second type is we can replace a row by a scalar multiple of itself. So we replace the ith row by k times the ith row. And the third type is we can add a scalar multiple of another row to a row. That is, we are replacing ith row by ith row plus k times the jth row. So suppose we start from matrix A, and we perform one of the three elementary row operations, and we get to matrix B. Then how is the determinant of matrix B related to determinant of matrix A? For the first type, if we interchange two rows, determinant of the resultant matrix equals negative of the determinant of the original matrix. And if it's the second type, if we replace a row by a scalar multiple of itself and we get to matrix B, then determinant of B equals to the scalar times determinant of the original matrix. In the third type, when we add a multiple scalar of another row to the row, then the determinant of the resultant matrix remains the same. It equals to determinant of the original matrix. Now let's look at four examples. In the first example, we have a generalized 2x2 determinant with entries A, B, C, and D. And suppose we perform the third type of elementary row operations. So we replace row 1 by row 1 plus S times row 2. Then we get A plus SC, that is the first entry. Then B plus SD. And second row remains the same, C and D. Determinant of a 2x2 matrix, it is the product of the opposite entries minus the product of the other opposite entries. So, A plus S times C times D and minus the other product, B plus S times D times C. Let's expand this. We get A times D plus S times C times D and minus B times C minus S times D times C. And note that the second term cancels out with the fourth term. So we are back to A times D minus B times C, which is the original determinant. A, B, C, and D. And now we verify the third theorem. When we add a scalar multiple of another row to the row, then the determinant remains the same. Now let's look at the second example. We can factor out a constant from a row. For example, for this matrix, the first row, they are all multiple of 2. So I can factor out the 2, and row 2 and row 3 remain the same. So this determinant would equal to 2 times the determinant. 1, 2, 3. 1, 2, 1, and 7, 3, 1. So this is unlike scalar multiple of a matrix. When we times a scalar to a matrix, we have to multiply the scalar to each entry. But for determinant, we can factor out a constant from a single row instead of the entire matrix. And why is that true? That is from the second theorem. Let's call this matrix, matrix A, and this matrix, matrix B. So we get from matrix A to matrix B by replacing row 1 by 2 times row 1. So from the theorem, determinant of B equals 2 times determinant of A. Now let's look at the third example. Here the first row is a multiple of 2, and the second row is a multiple of 3. If we don't factor out the constants, we can find the determinant is 18 minus 12, which is 6. But we can also factor out the 2 and 3 from the rows. So, the 2 from row 1 and the 3 from row 2. Then times the determinant, 1, 2, 1, and 3. Which equals 2 times 3 is 6. Then times the determinant of the 2 by 2 matrix, 1 times 3 minus 2 times 1. And we get to the same result. The determinant is 6. Now let's look at the last example. It's given that determinant of A is 10. And we perform 3 elementary row operations on A to get to matrix B. And the question is, what is the determinant of B? The first elementary row operation we perform is we interchange 2 rows. So when we interchange 2 rows, the determinant of the new matrix would be the negative of the original matrix. So negative 1. Then the second elementary row operation we perform is we add a scalar multiple of row 2 to row 1. And when we perform this type of elementary row operation, the determinant of the new matrix remains the same as the determinant of the original matrix. So we have a positive 1. And the third elementary row operation, we replace row 2 by twice of row 2. So we are replacing a row by a scalar multiple of itself. So the determinant of the new matrix would be twice of the determinant of the original matrix. So times 2. And finally times determinant of the original matrix A. That is negative 2 times determinant of A is 10. So determinant of B is negative 20. And that is the end of the lecture. If you are interested in the complete course of my linear algebra course, I'll put the link down below. If you like my videos, please like and subscribe, and I'll see you in the next video.